Okay, this is a short summary of lecture 2, just finished in offline. So the lecture 2 considers the thermal oxidation. So oxidation is producing a thin layer of silicon dioxide on the surface of a vapor. So of course it is used to make the gate oxide, or sometimes we wanted to have a very thick oxide for isolation purpose. Its chemical reactions can be found in two different ways. First we have silicon, and here we have water vapor, and here we have silicon dioxide, and as a byproduct we have hydrogen gas. In this case we have water vapor as an oxidant, so it is called as wet because it contains water. However, in the case of the second example, silicon and oxidant O2 gas is directly used, and we have no byproduct and silicon dioxide is formed. In this case, we have no water vapor involved, so it is called as dry oxidation. It is noted that result of these reactions we have amorphous silicon dioxide. Its weight density is about 2.2 gram per cubic centimeter. Compared with crystalline SiO2 quartz, it is much lower weight density because crystalline SiO2 quartz is closely packed, and amorphous silicon dioxide has loosely coupled atomic structures. So now let's consider kinetics, and this diagram can be helpful for understanding the procedure. Here we have ambient and oxidants. In the case of wet oxidation, this is water vapor, and in the case of dry oxidation, it becomes the oxidant gas. And here we have already formed oxide layer, and we have silicon. So in order to make silicon dioxide, of course oxidants and silicon should meet together. However, in the case of silicon, they are just bounded in the silicon crystal, so they cannot move. So the only way is these oxidants come to the silicon. Then what happens? In this case, oxidant should move the surface of oxide layer. After that, that is inside the oxide layer, and they should diffuse. Finally, when the oxidants arrive at silicon dioxide interface, the reaction happens. So we have to consider these processes. Also, it is noted that since silicon's atomic, so per unit volume atom numbers, and silicon dioxide per unit volume molecule number are different, so we must have 25% volume expansion. If we have three-dimensional oxidation, then length will be increased slightly. However, usually we wanted to have one-dimensional growth of our oxide growth oxidation. So usually this 125% volume expansion is just copied into increase of oxide thickness. So there are many parameters related with the oxidation process. So first, oxidant species. As I told you before, there can be two different ways to make silicon dioxide, dry and wet oxidations. In the case of dry oxidation, we have a low oxidation rate. It means that after a long time, still we have a very thin oxide layer. Instead, the material quality is good, so it is mainly used to fabricate high quality oxide layer. On the other hand, in the case of wet oxidation, it is much faster than dry oxidation. However, the material quality is not as good as the one by dry oxidation. The higher speed is mainly due to the oxidant solubility limit. Simply speaking, water is more well solved in the silicon. Now, let's go to the effect of temperature, pressure, and crystal orientation. In the case of temperature, of course, if we have a higher temperature, oxidation rate increases. Also, under the high pressure, oxidation rate increases. Also, crystal orientation have some impacts on speed of oxide growth, and in the case of 111 surfaces, it is faster than on 100 surfaces. So since this course is a computational one, so we must consider certain model for this oxide growth. So most well-established one is a so-called Deal-Grove model, and that was published just almost 60 years ago. This is really old model. However, this is well established, and due to its simplicity, as a first guess, it is still widely used. As I told you before, in order to meet the silicon, the oxidant should have some travel from the bulk of oxidant gas to the surface of oxide, and also diffusion inside oxide. After that, the reaction should happen. So these three cases can be listed as 1, 2, 3, and each of them can be modeled using the densities at a certain positions. That is done in this case. Please have a look at these graphs, and concentrations are written here as a C, capital C parameters. C star is bulk density of oxidants, and CO is surface density at oxide layer, and C sub S is also interface density between silicon dioxide and silicon. When you have this kind of configuration, the F1, F2, and F3 can be easily formulated in that way. So here we have some parameters like H, D, and Ks. They are all related with each process. And here we have XO is the thickness of oxide layer. So actually we wanted to understand the change or temporal variation of XO. So how can you do that? Now we identify three different fluxes And if everything goes quite smooth, then these F1, F2, and F3, F fluxes should be the same. So by assuming that these three fluxes are the same, then we can easily show that this flux can be expressed as this form. Important point of this expression is now density, only bulk density occurs. Why that is important? Because C star bulk density can be controllable parameter. The engineer can change C star. So this is quite understandable and known parameters. And here we have some unknown physical parameters like case of S, H, D. They are difficult to measure. And of course, oxide thickness, it is not that difficult to measure. However, in situ measurement is not that easy. So in this case, well, anyway, we kick out CO, CS parameters, and later all of these difficult parameters will be merged into just measurable parameters. So once we understand the flux of oxidants from the bulk to the interface between silicon dioxide and silicon, then we can understand the time variation of XO. Thickness can be proportional to the flux. Once we understand this relation, now in a simplified form, we can find out a differential equation, ordinary differential equation for XO. And A and B are constant related with these components like case of S, H, and D, C star, and N. Then you can easily identify what is A and what is B. Then now we have this simple standard form of differential equation. By integrating from t equals 0 to t equals to t, we can easily find that solution is given by this way. So now we have no longer time derivative is involved because we have already made the integration, and quadratic expression for XO equal to some time varying parameter. So here tau is introduced to describe the initial thickness of our problem. So since this is a well-known form, we can find an analytic expression for oxide thickness as a function of time. So simply speaking, if we know A and B parameter, and if we know the initial thickness of our oxide layer, then we can draw the oxide thickness as a function of time. Before going into the Python implementation, let's consider two limiting cases. One case is long oxidation. In this case, T is much larger than tau, so now this term can be simply regarded as this one. Also, here we have 1 and -1, that doesn't matter. So considering this approximation, then we can find that in this limiting case, XO follows square root of B times T. So it means that oxide thickness is not linearly increasing. So if although we have spend 4 times longer time. However, still we have only 2 times thick oxide layer. So simply speaking, in this case becomes sublinear growth, and this becomes very inefficient. However, if we go to short oxidation limit, then on the other hand, this term can be regarded as a small number, smaller than 1. Then by using the Taylor series, we can expand it as this way, first order approximation. Then by manipulating this approximation, we can find oxide thickness follows this linear behavior. In this case, time is increased, then now thickness is linearly increasing. Therefore, with these two Deal-Grove parameters, B and B over A, now we can well describe the oxidation process. So maybe you can ask me, where is the physics? Then of course we can understand A and B parameters consume the physics inside it, because A and B are all related with C star and Ks Hd, which can be a function of many parameters like temperature or pressure. And table for B and A parameters can be found in textbook or research papers, so we can use it. So let me give you a simple example. Now think about dry oxidation at 1000 degrees Celsius. This is quite a typical case, and in this case the Deal-Grove parameters B and B over A are given as this way. This is not my invention, so I took it from other examples. So this is quite a typical number, and now let's assume that time constant is given by 0.37 hours. So of course, depending on the situation, your initial condition, it can be different. Then using the Python, you can simply calculate the thickness as a function of time, and also draw the thickness as a function of time. So it is quite simple. First, import some necessary libraries and define B and B over A parameter and tau. They are given from our example. After that, time is set from 0 to 1. And what is 0 and 1 means? 0 is corresponding to the initial time, and 1 in this case 1 hour. After that, thickness is prepared, and actually thickness is calculated. You can easily understand this expression is mere implementation of this Deal-Grove model. Then after that, we can draw thickness as a function of time and setting labels and range of axes, and we can show it. Then this is the result. So we have grown up to 1 hour, and this is the thickness. If we wanted to have just 40 nanometer thick film, then how long should we run this oxidation process? 40 nanometer is corresponding to 0.04 micrometer, and you can find that this is corresponding to this number. This is approximately just 20 minutes. Okay, so starting from about 23 nanometer thick film, then just run it in 20 minutes, then we will have 40 nanometer thick film. Of course, it is well known that the global model fails near 0 hour because in reality, in experiments, it is observed that the very rapid increase of our oxide thickness. However, our Deal Grove model cannot describe this superlinear um, oxide growth quite well, so we must a little bit modify it, but we will not consider it because it seems to be a little bit beyond the topic of our lecture. Okay, so this was a short summary of lecture 2, and unfortunately in this semester, since we have a small number of enrolled students, so maybe we have to close this lecture course. However, from time to time, I will occasionally upload my lecture material prepared for this semester. So this course will come back in the fall semester, and let's have a look at the lecture materials together with me. So from time to time. Okay, thank you for watching and see you later. Bye.